All right. We're okay with the mic? I guess it's just for recording. So welcome to this lecture. Dennis mentioned my name is Sergey Bykov. I'm a developer lead in Microsoft Research, and I'm going to be talking about Project Orleans, and I'm going to give two talks about it. So today's talk is more conceptual and architectural about what the problem is, how we're resolving it, how the things work under the covers. And the second talk tomorrow I'm going to give will be more about the practical use and the programming model and how you can actually use Orleans. So that's the plan. So a little bit about myself. Anybody knows what the building is in this picture? Just it's my litmus test today. Is there anybody here from my alma mater? Okay. What is it? Okay, excellent. So yeah, that's the Bauman Technical School, it used to call it. I know why we have these pictures. So I graduated in '95, and I joined Microsoft in 2001. 6 years later. The Microsoft is a big corporation. Even in Redmond, it's a huge campus. And what's interesting about it, you can change jobs within the company and move between very different things, like working on, say, Internet Explorer or work on Xbox or on phone. So you can change jobs without changing the company or changing your employer. So I use that opportunity to change a few jobs in the company. One thing I like to brag about that I'm one of the few people that can say that I ship my own version of Windows with a very small group of people. So if you're interested in details, ask me later how that happened. And in 2008, I joined a new lab in Microsoft Research. This is where I met Dennis. And about that time, we started working actually on the Project Orleans. And I've been working on it since day one, since the original idea. And it's been in production for, I guess, almost 4 years now. Been used in production by broader groups. And we keep developing it, and we have a public preview available outside the company. So they're real. And along the lines, we had several other projects that build on top of Orleans. For example, we had this project, Horton, the distributed graph database, things like that. So you probably heard already opinions about what the cloud is. And there is no clear definition, I guess. There are people have various different versions of the definition. So my attempt is to say it's really about on-demand computing. So instead of buying your own hardware, your own servers, put it in your lab or in your own data center, you sort of outsource hardware. You buy it on as-needed basis from somebody else. So it goes for compute, for storage resources, for network, for all of that. So instead of hiring your own people that would maintain and upgrade and fix your hardware, you give it to Microsoft, to Amazon, and even to Google. Say, you do this, I'll just run my application, my code, my system. So you pay a price for that. So unlike HPC, where you have your own cluster that you maintain, or people maintain it for you, you really lose control over what's going on with this hardware. You get these virtual machines, and they aren't really strict guarantees. So these machines can be up and down. They can be migrated. Very little really is guaranteed about their co-location, for example, or this problem of noisy neighbors. Somebody else, some other virtual machine can run on the same physical machine and take most of the network traffic. So there are all these things that is a result of this trade-off. So you don't want to spend your own resources, but you have to deal with reality you get instead. But the big promise of it is it's infinitely scalable, because you want to use 10 servers today, and you dream about growing into the next Facebook, for example. You can rest assured that you can get the scale of thousands or tens of thousands of machines later if you need, if your business starts catching up. So you don't have to invest upfront in the hardware. But because of this different paradigm of how resources are allocated, what kind of resources you get, you have to rethink how you build software for this new paradigm of cloud computing. And there are some new sort of unique challenges that emerged with cloud computing. There are also different ways to use cloud computing. Because the kind of intuitive way for us to do it is just keep using it as if you were running your local set of servers. For example, all this batch computation that you used to run on your own machines, you just upload them to the cloud and run. So that's what I call it. You can do your grandma's batch jobs. But there are more emergent trends that go beyond that. So people want to build interactive services, services that you get responses, you get your web pages, your mobile applications, your devices that can talk to the cloud, talk to the services, get responses within milliseconds or within seconds. So it's not a batch operation anymore, and it's a very different set of challenges how to build it. So to summarize, it's really about having high throughput, low latency kind of workloads. Because people, when they wait for their Google search or Microsoft Bing or Facebook web page, they don't want to wait for a few seconds. They don't want to wait for the batch job to run. Because you have potentially a very large number of concurrent users, you want to scale horizontally very far. So you can start with thousands of users, but 2 years from now, you may have millions of users, or if you're very successful, hundreds of millions of users. And you need to build your software that can scale that way, and that's not trivial. The availability is also a new requirement for business. So it used to be that people would shut down their services, say, we're in maintenance mode, so a service will be down for 6 hours or for half an hour. You cannot afford it anymore. So you have to run your software 24/7, 365, even though your hardware may fail. So these virtual machines or hardware or physical machines that run your system, parts of your service, they may go down, but your service, your user experience should stay and continue to work as if nothing happened. So there are really two categories of challenges. There are programmability challenges, how you have programmers write code, how you as a software developer write your code, how you solve this problem of for example, concurrency, distribution, partitioning. And for example, I'm curious, who enjoys writing concurrent multi-threaded code and debugging data races? Anybody likes to do that? Looks like there are no brave souls who would say, yeah, I like when I have a race condition in my code and I put a debugger and still have no idea what's going on. So this is even in a single process, it's challenging, especially the multi-core architecture. We have multiple threads running physically in parallel, not just time slice, but physically in parallel in different cores, effectively different processors. But now, if you look at this multiple threads running in a single VM, but also have many VMs running in parallel on different machines, so the concurrency is a much more daunting problem. You cannot attach a debugger to them. You cannot say, stop the whole system, I'll look where my call stacks are. So it's a different level of concurrency challenge, a parallelism challenge. To run on a large pool of machines, you need to distribute your compute. So what's the unit of distribution? How do you physically distribute it? How do you decide where to place these computations? How do you manage resources? How do you know that you're overloaded or underloaded? So how do you split your state? So if you have, for example, millions of users, how do you split physical data that belongs to these users across those machines? Do you partition the load? But once you partition distributed load, you need to communicate, you need to coordinate. So you have this many threads running on many machines in parallel, but they all do some kind of related computation. So you need coordination. You need somehow to synchronize what's going on. You don't want to have one thread updating state of variable from A to B just for another one to change it from B to A in being consistent. Failures, I mentioned, are norm in the cloud. The machines can fail, network may fail, anything may fail. So you have to program in resilient ways. So you cannot just say, oh, machine failed, I'm going to restart my cluster and rerun my job. You cannot afford it anymore, so you have to stay up. So programmers that have been successful building desktop single machine applications, even concurrent multi-threaded applications with primitives like locks and semaphores. So for them, it's a huge step to go and program for distributed systems. And there aren't really that many distributed systems experts in the world in general, because that's a set of a very hard problem. So one approach is to teach them, to take a large pool of general desktop developers and make them distributed systems experts. And that's proven to be very difficult or almost impossible, because just complexity is too high. The other approach is to lower this bar, that kind of step function and say, we will have a set of tools in the program model that allow for a regular developer just make a small step up and be successful in this new cloud and new distributed world. So that's the approach we've taken. So the operations aspects today are as important. Who has heard the term DevOps? Anybody among the students? DevOps. So it's a new paradigm where there used to be developers would write their code and then throw it over the wall to, say, testers. Testers would run some tests and say, oh, yeah, this build is OK. And that would give it to operations people called ops. And those operations people would deploy to the actual physical machines and monitor what's going on there. And if something goes wrong, they would have a pager beep and say, oh, this machine failed or this service is unavailable. And these ops people, poor ops people, would spend their duty at 24/7 managing the service and solving issues. So that paradigm lived for, I don't know, 15, 20 years, and it's almost gone by now. So now it's developers' responsibility to be on pager duty. It's their responsibility to monitor. They take turns usually. So you assign like once a week or once every 2 weeks. There's a day that you're on duty and you carry a pager or cell phone, doesn't matter, and you get called when something goes wrong. When your production service, when something fails, it's your responsibility to go log in, connect, fix it, restart, deploy an update or something like that. So the resource management is another aspect. It's one kind of a grave failure. So if your resource is overloaded, you need to maybe add more virtual machines because your CPU utilization is too high, your latency is going up. So like I said, that used to be a responsibility of separate kind of category of people, operations, they call it operations people. Not anymore. Now all this, in most of the companies that run online services, there's notion of DevOps. Every developer is responsible for running and supporting their code in production. The idea behind is that the more developers are paged or called at 3 a.m. About a problem, the better code they will write, the more resilient code, the more safe code they will write, because it's they will be on the line if something goes wrong. Who is familiar with the term A/B testing? Okay, a couple of people. So that's another technique that is pretty common in the industry now when, say, you run a version of your service, I don't know, Google search or Facebook or Bing, and you want to make some change to the algorithm. You want to maybe some change to the user experience. So instead of going and rolling out a new version, what you do, you allocate a small percentage of the users. So you deploy a new version sort of side by side with the current one, and you redirect traffic for, say, 1% or 0.01% of all users to go and use this new version. And you monitor and understand, is there any problem with the new version? Are people happy? Are they using it the same way as they've been using the old one? So you kind of test it in production instead of running tests within your lab and then rolling it out to everybody, potentially breaking everybody or making people unhappy. You roll it sort of in a very small scale, side by side with the main version, and you use your users as guinea pigs and measure how much they like this new version. So again, you need tools, and that developer's responsibility to do that. So it's the brave new world. Things change. How online services, cloud systems are built and managed. So just to give you one real-life example from our experience, who is familiar with the Halo game for Xbox? Okay, a few people. Good. So that's probably the marquee game for Xbox that made it successful initially, and they keep releasing it every few years. It's a very big franchise, making hundreds of millions of dollars within the span of a few weeks. So that whole gaming business is very movie-like, where in the first few weeks they made more money than for the rest of the year. So they have this interesting challenge where they have a very large number of users. So they sold, I don't know, 30 million or 50 million, I don't know the exact numbers of copies of the game. But all those people are not playing the game at the same time. Some of them bought it, played it for a few weeks, and just don't do it. Some play on the weekends, some play around the holidays, some play very hard when there's a new version. So they need to manage a smaller population that keeps changing over a period of time. And it's very dynamic. So the game is joined, the multiplayer game is the most interesting aspect. It's joined by up to 16 players. So they play for a while, maybe 10 minutes, 20 minutes, and they go on and they start a new game. So the relations between games they play and players and their friends, it's very dynamic, very fluid. And so they need to run this hundreds of thousands or millions of games at the same time while all these people change affiliation as they join groups and join games at any point in time. So what's also interesting, they store all the data about every single game played from Halo 1, from, I don't know, it's more than 10 years ago. So we really store very detailed statistics about who did what and who killed what enemy, what weapon, because that's a trove of data for them to analyze even today. But also their users, they expect to see all these details online. So they play the game, they want to go and see how did I do compared to my friends? Who is the top player? What's the leaderboard? And this is just a real example from their website of how much data they show there, statistics about the games in different categories. So this data needs to be stored. It's a huge amount of data. So like billions of games that have been played since the beginning, and they need dynamically displayed in the view like that for their users in parallel for many users that go and check it out. So this is another challenge that is specific to the gaming industry that, unlike with most other online services where the popularity of a service grows over time. So initially you have very few people that learn about your new something, your new service, and then they tell their people they're happy, so their friends join, learn about, start using it, then it gets into the media, and more people want to use it. So over time, your usage grows. So you kind of have some sort of line or curve going up. So that gives you an opportunity to change your implementation, change your decision, your architecture, your design of your system as your usage grows. It's still very challenging because if you can't keep up with the load, you have a problem. People will be unhappy. But in the gaming industry, it's very different. So when they release a new version, for example, of Halo, they have a very dedicated fans, and they go and line up on the street because they start selling at midnight in New Zealand. I think this is where it started. So people wait there for hours just to get the midnight in the store, get the game, run home, put it in the Xbox, and start playing. So all these people, starting with New Zealand, Australia, and further on around the globe, they start playing the first day, first few hours, and they stay very engaged for a few weeks. So their usage spikes right like vertically. It's not a curve, it's not a line, just it spikes vertically. And if you cannot sustain this load, if you cannot scale at that point, this first day, first few weeks, they're extremely unhappy. They're unforgiving. You're almost out of business at that point. So you don't have a second chance, essentially. So with those sort of challenges in mind, I hope I gave enough background. This is how we approached the project release when we started. So we wanted to focus on two priorities. One is developer productivity. So we can take a reasonable developer who can write reasonable code and make them successful. So they don't have to solve distributed systems problems. They don't have to understand Paxos or a complex algorithm. Even most experts don't understand, can see if that's right or wrong. And make them successful in building this high throughput, low latency interactive services that are in demand today because of kind of general web services, because of things like mobile applications, gaming, very popular. The emerging wave is called, who's heard of Internet of Things, IoT? So the new wave, I don't want to call it hype, but it's a new thing that is very serious in the industry, is Internet of Things, where you have a very large number of sensors or devices deployed in some area, and then some data to the cloud, and data gets analyzed in real time or in some other modes. But you have to deal with this very large number of sensors. For example, connected cars is one example. We have millions of cars that drive on the road and keep reporting information about their engine statistics, or whether there is something that indicates they need a repair. And this data gets flown to the cloud service constantly in high volume and parallel by all the sensors. We're talking about one example where a seismic sensor, so you want to predict earthquakes, so you want to get very large set of sensor reading from large areas. So you want to deploy the sensor, very cheap now. They're connected. They can send the signals over the radio. So you want to deploy them all in some wilderness and then analyze the data that's coming in ideally milliseconds or seconds and predict that something is going on, that maybe an earthquake coming. Have that kind of fidelity of data. So scalability is a hard problem because in the history of this successful online services like LinkedIn or Facebook or Foursquare, they show very same pattern, a very similar pattern where they build something that scales up to, say, 100,000 players. And they're happy it works until they start getting more users and they realize they cannot incrementally improve their system. They have to go back, essentially scrap their architecture, re-architect the system, build it in a new way, in a more scalable way, only to get to, say, 10 million users and realize this is another ceiling we cannot penetrate. We cannot just incrementally refactor code. We have to go back and change architecture. And then they're able to scale to a higher number of users. So the history of these services show that they do it 3 or 4 times as the load grows. And that's the unforgiving time, because if you cannot scale, if you cannot re-architect, rewrite a system as you become more and more popular, you lose your competition. And that's partly what explains the failure of MySpace, for example, versus Facebook. They could not scale. Their users weren't happy that pages were loading slowly, and by the time they re-architected, it was too late. Of course, there are other factors, but it's just one example where it played. So the goal was to make it very simple for developers to use, but also make it in such a way that if you use this program model, if you follow a set of very simple rules, then your code in general will scale by default, scale through several orders of magnitude. So we wanted to organize in such a way that you don't have to necessarily think upfront about how you're going to scale it. Of course, you can always shoot yourself in the foot. You can always create a single thing that everyone tries to talk to. You can create a bottleneck in the system regardless of what kind of tooling you have. But we wanted to make it much more difficult to get into this situation and much easier to get out of it. So this is what our colleagues refer to this project. It's a programming model and the runtime for building cloud-native services. Cloud-native meaning that they're interactive, high throughput, low latency, scaled by default to a large degree, resilient to failures, so that they handle failures of hardware. So if we look back at how the industry has been doing online services, this is kind of all too familiar 3-tier NT architecture. Anyone is not familiar with 3-tier architecture? So it's okay. So the idea is very simple, very powerful in a way, that you have the first layer that are front-end services, usually web servers that receive requests from the browsers or from user applications, from mobile apps. So they receive calls, like now it's usual to use REST APIs for web service calls or just use HTML for web pages. So they receive these calls, they authenticate users if needed, and then forward this request to a set of middle tier, so-called middle tier servers in the middle. So this is where the logic runs. So the front end is just sort of authenticate requests and send them to write to the server, and that server needs to do the actual, it has the actual code to run against to fulfill that request. And then you have a storage layer where you actually store data. It used to be SQL databases, then the NoSQL trend emerged. They became column stores like Azure Table or Cassandra's of the world and those kind of solutions. But you have your durable storage. That's the third layer. So the approach is very simple. To scale will be stateless. So whenever a request comes into, say, middle tier server, it says, okay, this is a request for user X. I'll go ask storage layer to bring me data for user X. For example, user profile. I want to update, I got a request to update the address of the user. So I'll load profile of the user, apply the update, and then call to store it back. Right back. Very simple. I can run it on any server. I can add more servers. They will work in parallel exact same way. So it worked fine for, I don't know, 10, 15 years because the load was much lower. They could afford to go and fetch this state from storage layer on every request. But as it started, the requirement came to support tens of millions, hundreds of millions of users, and the expectation of sub-second latency, storage became the bottleneck because it cannot serve that much data because you're constantly moving data back and forth between middle tier and storage. So you also refer to data shipping. And then storage has limitations. SQL databases limits, NoSQL storage have their own limits. So that's the bottleneck for your throughput and latency. Because even if, so I process a request to update the user address and say another request comes for the same user profile to the same server, it doesn't matter. I'll have to go and read it again because the moment I've finished processing a request, I forget that I just did it. And there is no state in memory that stays between requests. So that's what the model is stateless. So people realized that was the challenge, and the industry is very smart and very good at coming up with solutions. So they added a cache layer. Who's heard of memcached? So that's the popular caching solution. There's also like Azure Cache and Redis. So essentially, they said, okay, we're going to cache data in memory. For reads and writes, we will not go to, say, SQL. We'll just go there first time and then store it in memory in this cache layer, and all subsequent requests will go and be applied against the cache layer. Because now if second request comes for the same user, I already saved that user's profile in the cache entry in this layer. And the second request can be served essentially from memory. Still, there's network traffic, but it's much cheaper, much faster than go to, say, SQL database. So it's very good performance-wise. The problem is you lost all the guarantees, concurrency guarantees of your storage layer. In SQL, you could have stored procedures or just general SQL statement to guarantee consistency of your update. So if you are updating 3 tables or 3 fields in the same table, you can do it atomically and guarantee that the request will not interfere with another request for the same row in the table or a set of rows in the table. With cache, you lose all these guarantees. You get just read-write operations. You can read value and write value. And so if there are, say, 3 middle-tier servers doing concurrent operations against the same user profile, they'll just override each other, or they have to build their own consistency protocol, which, again, is not a trivial task. And that's not what you need at the application layer to build consistency protocols. And you're still shipping data. It's less obvious, but your code runs on middle-tier servers, and you have to ship data to them, even if it's from cache. So instead of shipping functions, say, apply this operation like you would do with, say, store proxy. Just send this is a command, apply it. You're still shipping data between all the servers. And interestingly, as in some other aspects of computer industry, computer hardware, gamers were some of the first people to realize that it was not working for them. And for their much more interactive workloads, they rediscovered this approach, the actor model, which was invented really in the 70s, 1973. There was a paper published on the actor model, which was published as a concurrency model, where instead of using locks and semaphores and this kind of synchronization mechanism across threads, instead you express your computation instead of independent, isolated items, call them actors. So it's really like an object that doesn't share state with any other object and talks to them via message passing by sending messages. So each individual actor doesn't run concurrently, really, doesn't execute concurrent request, and nobody can access directly and change its states. Instead of you receive the messages and you process them as they arrive. So the actor has this kind of atomic control of its state. But it so happened that its model also is very compatible with distribution because you have no direct memory sharing and you send in messages, then it doesn't matter really if you send a message locally within the same processor, send it over the network to another processor, another machine. So the model was really very good fit, surprisingly, 30 years later for the cloud workloads. And people rediscovered the most popular implementation of actor model was Erlang, done by Ericsson in the 90s. And people started building Java sort of ports of it. There's a project called Akka. But there's still problems there. Like one of the big problems is controlling how creation of these actors happens. So you still have parallel requests coming to the front ends or your middle tier servers. And in my example, when I want to update an address of the user, they go and check if there is an actor for that user in the system. So you go in and talk to some kind of actor directory that you need to have, and it tells you, no, there is no actor for this user in memory. Okay, so I checked, there is none. and I decide to create one. So I need to create an actor in memory for that user that I need to process a request for. Interestingly enough, in that system, you need to pick a server where to create an actor. So you're already making a resource management decision, even if you don't realize, because how do you decide where you go? Your application needs to pick a server. But that's OK. So I decided to place it on server A. And I need to register the fact in the actor directory. Say, I just created actor for user X on server A. But concurrently with me, there may be 3 other servers that receive requests for the same user. And they did the same check. They also tried to look up actor for user X, and they got the same response that, no, there is no actor for user X in the system. And they independently, in parallel with me, decided to create new actors. But they made different decisions where to place them on server B, C, and D instead of my decision to place it on server A. And they tried to register the same fact with the system, and somebody will lose, and some failures will happen. So we talked to some of the Erlang developers, and that was, interestingly, one of the biggest complaints, that this is one of the biggest, most common pitfalls, because this kind of failure happens only when you have concurrent requests. So you test on your machine, you test on your cluster, everything works fine. And you put it in production, and suddenly, boom, everything blows up because you suddenly got a race with creation. So we didn't want to go down that path. So here's what we came up with. So we called it virtual actor. So we published tech report where we changed this approach to placing actors. We said application code should not need to think about creating actors, or on the flip side, deleting them from memory. Because once you create this actor, this object on one of your servers, somebody needs to take it down at some point in the future. So in the traditional approach, that's the responsibility of the application code. We said that should not be the case. That's just insane. We started that way. We added this create actor, delete actor, but then we said it was really difficult to program against. So we came up with this model where actors virtually exist the whole time. So for example, you have this type of actors like user profile, as I was talking about. And they have identities. For example, use a GUID as identity of the user, or it can be an integer or a string. And then in our model, you can make a call. You can send a request to that actor regardless of whether it's in memory or not. You don't need to know. Actually, you don't even know whether the actor is in memory when you're making the call. So you just call the runtime and say, I want a reference to actor for user X. And you make a call immediately. The system, the runtime, our runtime, understands that there is a request for this actor, goes, looks up in its internal directory, makes all these decisions, resolve all the races, and then eventually creates this actor if it's not in memory anywhere, and delivers the request. Or if there is already an actor in the system, it just routes the request to that actor and executes there. So it's a very different approach to resource management as well, because now the runtime is in charge of the decision where to create. So the runtime has information about utilization, for example, or locality of different actors, and it has the opportunity to make these decisions to optimize placement and even optimize later. For example, we've done the internship that showed very promising results where we analyze what actors talk to, which actor talks to which actor more frequently, or a very chatty interface, and then we can move them together, put them on the same machine without application code knowing, because from an application code perspective, nothing changed. They keep talking to this virtual actor with identity X, and the fact that move from one machine to another machine between 2 calls, it's completely transparent. So it's complete location transparency for the application code. We chose .NET, well, of course, partly because we're Microsoft, but also because we think that's the best language that's out there to write this kind of systems. And Java people admitted that C# is a better language. So it was a good combination. Initially, there was the thought that we would create a new programming language. We even had a name for it. We call it DC#, distributed C#. But then we very soon scrapped this idea, said, no, developers will not want to learn a new language. They're already overwhelmed with the frameworks that are given, all the kind of new paradigms. A new language, people will just ignore it. And that's sort of the story with Erlang. It's very fine language and fine ecosystem, but it's a very small percentage of developers that use it because it's just difficult to move to a new language. So we decided to make it, again, aligned with the goal of making it easy for developers. So we decided to use just .NET interfaces, .NET classes. So when you declare your actor, effectively you declare an interface, like this user profile, just declare, and I'll show tomorrow in more details. So you declare an interface, and then you can have one or more implementation of that interface. And you can have an actor class that implements multiple interfaces and use that way. So it's very similar to just having interfaces and classes of objects in your normal single machine application. One restriction what we put up front into developer space is everything has to be synchronous. Because this idea of making a call to another machine synchronously and blocking the thread when you make a call, that's just evil. That should never have been done in the past. Synchronous RPC is a really terrible idea because threads are precious resources, and blocking a thread just to wait for, I don't know, 100 milliseconds of making a call somewhere else, even if it's a 1 millisecond, you're wasting system resources. So we decided that everything has to be async, and in C#, luckily enough, later, a couple of years after we started, was added support for this async await keyword. I'll show it tomorrow. Another big decision we made was about error propagation. So imagine a situation you have actors A, B, and C. So the request comes to the front end, to your web server. Web server makes a call to actor A, for example, the game, right? And the game makes a call to a player, actor B, and player needs to make a call to some other actor, player C. So what should happen if there is a failure in this call when the actor C executes the call? For example, throws an exception. So what we did, if the exception is thrown, you can catch it if you want. But if you don't, that exception will be automatically propagated to the caller. So the caller, in my example, actor B, will get an exception from the call to actor C. And it has a choice to either have try-catch around it. Again, I'll show code tomorrow. Or if it doesn't have any error handling, it just does nothing, that exception will be propagated to its caller. So if you put no error handling code in your actor code, the exceptions will propagate through the call chain, kind of like through a call stack in normal application. So when you throw an application in your normal call stack, it bubbles up to kind of one layer up and up until there is a catch statement somewhere. So it's kind of the same idea, but now it's horizontally, it's distributed asynchronous call stack. And in many cases, it makes sense to put exception handling only at the front end layer, at the web server. So if something failed, you don't really care. You cannot handle those errors mostly, but you will not lose failures. So the worst thing you want is to lose failures, lose exception. So we made it automatic error propagation. We thought it's a very, very important feature for people. So to sort of differentiate from other actor model implementation, we chose a term that we call our actors grains, so that we have certain set of guarantees, certain features of the programming model that are different from others. So we call them grains, so there is no ambiguity. Instead of calling them actors and people assuming what is not actually there. So we call them grains, and we needed a container, and we call container silos. So kind of big buckets of grains that run grains. And silo is the execution runtime. It's the process really that hosts a large number of grains and executes their methods, their calls to them, and does all the system work about messaging, delivering messages, serialization, deserialization of data, and multiplexing communication channels. So just kind of to visualize it. So there is notion of a grain, and grains run in silos. This picture shows like 4 of them, but in reality you can pack hundreds of thousands, in some cases millions of grains into a single machine silo. That's a really large number you can put there. And then silos, they form a cluster. So when you deploy your code, start silos on a bunch of machines, they automatically find each other and establish cluster and start monitoring each other. So if one of the machines go down, for example, it got rebooted for patching, or there's a hardware failure, a set of other machines, other silos in the cluster will detect that happened and will exclude that silo from the cluster and make the adjustments to resource placement, resource management. So it's kind of at a very high level. So this is to highlight. So you have a grain type, which is a class, really, of grains. Like, for example, the user grain is the class. Then you have instances, user grain of particular user X, Y, and Z. And that's where usual, like a traditional actor model stops. So we added this third column, which is activation of that particular grain. So the middle column, these grains, they exist the whole time. They're not physical, they're virtual, they're logical entities. So they all exist forever. They're never created, never deleted. And only activations, the third column, are created dynamically by the system to instantiate the particular grain on as needed basis in the garbage collected when it's not needed, when it's idle for a while. So this is just some poor animation that shows that we have this cluster of silos that run a bunch of grains. And like I said, it's much higher number than circles in this picture. And then there is a new silo that joins the cluster. It can be started at any point in time. Again, it joins the cluster automatically. You don't have to. Application is completely oblivious to that. And the system, the cluster recognizes there is a new server in the system and start placing workloads, start placing grains in that new silo. So if one of the silos become unavailable, for example, blows up or just gets network partitioned, it's get adjusted. And grains that used to be on that silo, they get placed somewhere else. So they get dynamically reallocated, transparent to the application code. And then if that machine comes back, it'll join the cluster again, and new placement will happen to that machine as well. So just to summarize, grain instances, like, they always exist. So for all potential users in the system, you have a grain that virtually exists. You never create, never delete them. Because of that, they never fail. There is no notion of a failure of a grain. Your call to a grain may fail. For example, you made a call and the message was sent over the network and there was a network problem. So you'll get an exception, like a socket exception back. Your call failed. But if you keep trying, eventually your call will succeed because the grain will never fail forever. It never actually failed. So that's a different approach to error handling and writing code for that. And activations is this physical embodiment of a grain. They get created on demand by the runtime. So if there is, we maintain an internal directory, and if there's already an instance registered somewhere in the system, we'll just route a request to it and create new ones if there isn't one already. In some cases, we can even create multiple activations, multiple instances of the same grain. If, for example, we declare a grain is stateless, and it's okay to create multiple concurrent instances on the same machine on multiple machines. Even that is possible. And I think I talk about location transparency enough. But Dennis, how much time do we have? Because we started later.
You have a half hour.
Okay, so because I was not sure. Okay, that's good. So this is another key feature of the programming model is the execution model. So so you wrote your code for your grain. Question?
So the user actually doesn't decide when to activate or disactivate, right?
Yes.
So, but how does the system guess when one should deactivate grain that is no longer used?
Thank you. Great question. How does the system decide to deactivate? So the default mechanism is time-based. So you can specify globally or per grain type what idle time you want to wait. For example, you said, I want a user profile grain to be deactivated after 20 minutes of idle time. So you specify it in config time when you deploy. And the silos, the runtime that hosts the grain, they will see, okay, when was the last time I sent the request to this guy? And if it was more than 20 minutes ago, I'll just garbage collect and remove him from memory. So that's the default mechanism. You can also, there's also a way for the grain to make a call to runtime and say, I think I'm done. You can deactivate me now. You don't have to wait 20 minutes. For example, you did some one-off computation. So you send Monte Carlo simulation. It's done with the simulation. It knows that it doesn't need to be invoked the same next time. You can just expedite and say, you can garbage collect me as soon as you can. So you can help that. Okay? So the execution model. So you wrote your implementation class for, say, the user profile grain. And you have methods that get invoked by the runtime. The key here is that you never get invoked in more than one thread. So whenever you call by the runtime, because the runtime that actually receives the message on the behalf of a grain and then makes an invocation, we guarantee that you never be invoked on two threads in parallel, which gives you this nice property. All the variables you have within your grain, the grain is already isolated. It's not supposed to share memory with other grains. So you have exclusive access to all your variables. And it was interesting, we've seen it more than once, where experienced, I would say, expert developers start writing code in Orleans, and their first inclination is to put the lock. So they receive a request, they need to update the user address or some list of friends, for example, of the user of the social network. So their instinct is to put the lock around, say, collection of friends or some address object, then make those updates and then release the lock, because they know there is concurrency danger in general. And so when they learn that they don't need to do this, that whenever they get called in Orleans, they don't have to worry about logging because they will never have any data race. That's a very liberating feeling for them, even for expert developers. Now, for non-expert developers that would have troubles writing multi-threaded code, they just, even if they don't understand what's going on, they are protected from kind of a large class of failures, of mistakes or bugs they can have in their code. They never happen because execution happens on a single thread. But it may be counterintuitive that we don't actually allocate a thread per grain, because that would be very inefficient or even impossible. So we have, say, if a single silo runs 100,000 grains, we don't want to have 100,000 threads, because one, they're very expensive in terms of memory. It's very inefficient, a lot of threshing. But I don't think you can even create 100,000 threads in the Windows operating system. So instead, how it works, the runtime has a very small thread pool for executing requests. And usually, it's one thread per core minus one for system work. And it's configurable, but usually that's the ideal number. So if you run on the 8-core server, we allocate 7 threads for executing grain requests, even if you have 100,000 grain activation within that silo process. So we'll multiplex execution, all these requests, across just very small number, like in my example, 7 threads. So effectively, that's cooperative multitasking. So you're not supposed to block threads. You have to be asynchronous. So there's some discipline that's needed here to only write code in an asynchronous manner. But you get, as a result of that, you get a very good performance, because you're not wasting system resources. You're not thrashing caches and memory. It's a very efficient model for execution. Just a glimpse of the grain developer experience. Like I said, I'll cover it in more details tomorrow. So I mentioned the interface. This is how you define a hello world in Orleans. So first you define an interface for your grain, call it I hello grain. And you see there are 2 things that are highlighted in red. One, the interface has to extend the marker interface I grain. There is nothing there, it's just empty, just to indicate I hello grain is the grain interface. And the asynchronous requirements is that every method on the grain interface has to return a task. Who is familiar with task parallel library task? Okay, that's good. So if you're not, I would really encourage you to read up tonight about task parallel library task, how to use them, await async keywords. This is really magic that is nowhere else. I've been presenting about Orleans in various forums. Like I was at the HPTS workshop, which is very kind of by invitation only in California. And I was telling people how we use it, and that we use these keywords in C# async and await. They couldn't believe me. They were suspecting I was fooling them. I was telling them that was not true. That you couldn't have this to write code that looks synchronous but executes asynchronously. So it's really, you need to read it tonight. That's a really fascinating thing, how that is done. So when you define a class that implements grain, you need to do 2 things. You extend the grain base class that we provide. I'm renaming it right now to just grain. So that indicates that this is a grain class. And then you implement one or more grain interfaces. In this case, the interface we just defined on the previous slide. And in this example, I have a private variable that keeps counter of how many calls I receive. And when the request comes, say hello, it returns a response with another string and increments the counter. So the counter doesn't need to be protected. I don't need to put a lock around the counter or lock around this grain because I will never execute this method on more than one thread. So it's safe, and because I don't need locks, it's efficient because locks are generally expensive. So of course, this is just hello world. There's much more than that there. So this is how somebody who calls the grain, and in this case, it may be another grain that makes a call to this grain, or it may be your web server, your front end makes a call to a grain. This is what it needs to do. So the first line is only for non-grain call. This is for like your web server, web front end, to initialize the client. The client is something that runs outside of Silo. If this call runs within the grain, you don't need the first line. So the first line kind of sets up the environment on the client just once to declare configuration, connect to the cluster, and things like that. And then the second line is the most interesting. You see this hello grain factory. So where does it come from? It comes from the code generation step that happens when you compile your grain interface. So we define, go back. So when we define this interface in the Visual Studio project, when you compile it, we auto-generate the factory class just using naming convention. So we drop I, we take hello grain, and add factory after it. That's how you get hello grain factory generated for you. And the key method there is getGrain, which returns you what we call grain reference. It appears like an object reference. It's not obvious here, but grain ref variable, it implements the original interface, I hello grain. So you get effectively proxy object return here. So getGrain takes an argument which is identity of the grain within the type. So in this case, the type is hello grain, or whatever type implements I hello grain. And the identity can be either GUID or integer, what I'm showing here, or it can be also extended with a string. Like for example, in many systems, user identities are GUIDs. So whenever a user registers, there's a GUID assigned. They're unique and all this nice guarantees, very compact. So GUIDs are very natural to use as identities. In some systems, like in Halo, they use long integers as identity for a lot of objects. So it's very convenient for them to pass a long, which is effectively 8 bytes out of 16 bytes of the GUID. It's half a GUID, really. And so what's interesting that this getGrain call may not be obvious, but it doesn't send any messages from the machine. It just locally manufactures this proxy object with identity of the grain. So there is no waiting, there is no blocking here. It's a very fast operation, just manufacture an object. And then you call a method. So grainRef, like I said, it implements the hello grain interface. So it has say hello async method that we defined on the interface 2 slides before. So you can make a call right away. So you're not checking whether this grain is in memory or not, just making a call, and that's it. And let me jump back again. This is how we define the method. So we're making the call, and what we're getting back is the task of a string. So another way people call it is a promise for a string. The task of a string is a promise that is returned immediately. So it's a local call. Say, here's a promise for a string. The result will come sometime later. It may come milliseconds or seconds later, but the promise is returned right away. There is nothing for you to do until the actual string is arrived, and the promise, this task, is resolved with the value. So it stays unresolved until a response comes back. And this magic of the wait keyword allows you essentially to suspend the execution of your code until that response arrives. So the reply is really of type string. I should have put types here. And it will be initialized with the return value of a grain, probably a millisecond later. But we don't want to block a thread for a millisecond because for a modern CPUs, millisecond is eternity. So what await does, it really takes the rest of the method after it and creates a closure or a continuation at compile time. So compiler does this magic. And just puts on the side, allocates the closure object, and sets it so that it will execute it when the response comes back. In the meantime, the thread is released back to the system. So we're not blocking the thread here, even though we write code as if we're blocking. So that's the magic that the cool kids in Silicon Valley couldn't believe me. There was even Eric Brewer was giving a talk, the guy that sort of coined the CAP theorem for distributed systems. He was talking about this challenge of giving developers asynchronous programming model. And I told him we solved this problem, Microsoft. He didn't know. He didn't know that this magic already existed. And so await breaks execution in two parts. And when the response comes back, reply variable will be initialized with actual string return, and then we can print it or continue execution, whatever we want to do with it. A glimpse of what really underlies this program model, because I've been covering more of a developer experience of what's exposed in the program model, but I'm guessing you're curious how this works. So this is a kind of high-level picture view of the runtime. So this fancy, colorful sets of blocks, they're silos. They represent the silo. So one is shown bigger, and there are three on the side that are just smaller. So at the lower layer, there is a messaging, a set of messaging components that are responsible for establishing connections. And physically, what we do, each silo opens two TCP ports when it starts. One is for communicating with other silos. And each silo connects to each other silo in the cluster, every other silo in the cluster over TCP right away. So for example, if you have a 100 server deployment, 100 VM system you deployed, and you have one silo per virtual machine, so each of them will connect to 99 other silos by opening TCP connection over that port, which intuitively things like a lot, right? So everyone connects to everyone. But if you compare it to the other alternative of opening TCP ports or registering URLs for each individual grains, and we can have millions of them in the system, 99 connections, 99 TCP sockets open, it's really a very small number compared to, say, millions of URLs. And so what happens at this layer, any messages that go between silo A and silo B, any grain that lives in silo A and makes call to silo B, they all go over the same single TCP socket. So we don't open more connections. And that's actually very efficient compared to what people do today. We also do serialization of messages. So if you saw in the interface, you just declare a normal C# interface. The requirement there is that arguments and return values, return types, they need to be serializable. And at compile time, we also generate efficient serializers for that. So the goal here is that developers that write code, they don't need to think really, they don't need to get into serialization business. They just send their normal types, and they magically get shipped over the wire, which is not a trivial task to do efficiently. So this is, I was talking about TCP port on kind of the right-hand side of this big silo. On the left-hand side is this client gateway. This is another TCP port we opened. This is for connection of, say, web servers, like the front ends, that they're not a silo, they're just some, from our perspective, it's a client code that connects to the system. The difference there is that, say, your web server that receives requests from, say, browser or from the mobile app for user X, it has no idea where a grain may live in the system. It's not plugged into internal data structures, distributed data structures. So what it does is that it just forwards the request to one of the silos in the system through the client gateway port. And silo that receives it is responsible for understanding and routing the request to the right destination. So in the middle, you see this box with activations, the grain activations. So like I said, we can have hundreds of thousands of them on a single server easily. It's really constrained by CPU or memory utilization of individual grains, and that's application code. But we keep track of them. Like I mentioned, we keep track when they get invoked so we can garbage collect them later. So all this. The question? Yes. So this set of color blocks is a single silo. And they have three more kind of zoomed out that it's connected to. So we keep track of all activations, and there are specifics like when they were invoked, and there's many more bookkeeping information that's there. The actor directory piece, the top red box, this is the distributed hash table, the special distributed hash table that keeps track of all the actors in the system, all the grains that are placed. And this is the thing that gives a response to whether we already have an activation for the particular grain or we need to create a new one. So it's a DHT distributed hash table that we implemented with specific guarantees that can only have one activation for most of the grain types. The cluster membership piece underneath, that's the one that is responsible for forming a cluster. So you start multiple silo processes on the multiple virtual or physical machines. All they need to share is same configuration, same deployment ID. So that means they belong to the same cluster. And they start asynchronously, especially in systems like Azure. There is no guarantee when a particular VM will start. There's no lockstep synchronization. So they can start minutes apart, but they form a cluster automatically. And like I mentioned, they start monitoring each other to see if they can still talk to a particular machine and vote. If I cannot connect, that machine didn't reply to 3 of my pings, for example, I can vote that I suspect this machine is dead. If another machine that also is monitoring votes the same way, then we may declare that that machine is dead and tell everybody else in the cluster, we lost this machine, all these grains that live there, they're gone. So if there's a new request and you create new activation of them, of those grains and things like that. So that's the cluster membership piece. So dispatcher is the obvious, I guess, piece that we receive requests over TCP or the network, and they need to dispatch it to the right grain activations. And there are certain restrictions and guarantees on reentrancy, and we'll talk more about it tomorrow. So activation catalog is kind of what keeps track of activations, of course. We have a built-in support for persistence. You can declare your persistent state within the grain. And this persistent manager, it has a notion of persistence providers, or plugins, so you can have essentially a driver-like model where you can decide to store a state of particular grain type, like my example of user profile in SQL database, if that's okay, or in some other storage. So all you need to do is to assign a particular provider and the configuration. So you don't have to write code against, say, SQL or non-SQL store. So we decoupled that. And the execution of all these components is governed by the scheduler. That's the one that has the worker threads allocated, usually 1 per core minus 1, but also it manages other like system messaging with some system priorities. So it's a scheduler that plugs into the TPL, task parallel library runtime. That's what allows us to intercept calls and this asynchronous execution of tasks and guarantee in the end that all execution for particular grain activation happens on a single thread. So that's a critical piece for that set of guarantees. This is the same information, but sort of in words as opposed to in picture. I think I covered it all. Since you're scientists, I need to show some graphs. So this is, remember, the second goal, first one was programmability, second was scalability. This is a scalability graph of the actual production service that Halo runs, one of their highest throughput services, that we run in our lab every night. So we run the tests and we measure throughput. So nightly we run 25 servers. But then at some point we test it on a larger cluster and we measure the throughput. And so 500,000 requests per second, that's really, you can double that number because that's 2 hops, 2 RPC calls between grains, between client and another grain and grain and another grain. So it's really, we're processing about over a million RPC calls per second on 125 servers in this case. But the key is that you see the line is pretty straight. So it's not, it didn't plateau. It was going up pretty nicely. We were surprised how good it was. So this is another graph. It's latency as a function of CPU utilization of the machine, which sort of highlights this point about cooperative multitasking. Because we don't have too many threads in the system, because we execute very efficiently, we stay pretty low in utilization until, so you need to look at median really, because 95th percentile, there's a reason why it goes up, because there are some relatively rare calls that are more expensive. But if you look at the median up to like 55 or 60%, there is no impact on latency. So you're in 10, 20 milliseconds, if I remember right. under 30 milliseconds. And then it stops growing. And we've been running this test in our lab with CPU utilization of 96% for hours. And it's stable. Again, because it's cooperative multitasking, we control it and be very efficient and not fall over when utilization is high. This is another graph of throughput is a function of number of actors in the system. Yeah, there is some degradation if you throw more and more actors because it's more expensive to maintain directories and other data structures that are a function of number of items in the system, number of grain activations. But you see, it's very modest. It's not like it falls off the cliff. This is another thing to highlight with cooperative multitasking. If we start increasing number of threads, so we artificially run this test with, instead of running on 7 threads, we configure it to run with 100 threads, with 1,000 threads, and this is what you get. So your throughput really goes down by, say, almost a factor of 5, or at least 3 or 4. So this is another thing that confirmed that our decision to have a custom scheduler with a custom thread pool was really good for performance. This is the graph that shows that the decision to make asynchronous calls and enforce asynchrony in the system is really paying off. Because, for example, oftentimes you receive requests and then you need to talk to storage, which is a long-run operation. So you can process calls between 2 silos in the system in under a millisecond round trip. But if you make a call to even fast storage like Azure Table, it may be 30 milliseconds, can be 50 milliseconds. But you're not doing anything while you're waiting for this 50 milliseconds to receive a response from storage. So technically, you can have a large number of those requests in flight using almost no system resources because you're not processing anything. So if you're asynchronous, if you're not blocking, if you're not really blocking your execution of other requests while you're waiting for this example call to storage, then it shouldn't really matter how slow your storage is. And in this case, you see we induced latency of 100 milliseconds or 1,000 milliseconds artificially, and it didn't impact the throughput. That's exactly what we want. That how slow the storage is doesn't really change your throughput. Any question there? Which is the standard approach? I don't think there's a standard here. Do you mean like a single process or distributed?
You said before you start the lecture, if I use actors, overhead exists for create and delete it, yes?
It's not in terms of.
Many actors, not one, not two, many. You very often create and very often delete and now overhead or not.
So you're asking about the overhead, if creation of deletion has kind of impact, the overhead has an impact on performance in that sense. Is that the right way of phrasing the question? So you're talking specifically about overhead of creation, no? Russian. We'll switch to Russian to make sure. Okay, we'll take it offline. So let me answer maybe different question that you asked, but sort of that reminded me. Yes, of course, there's overhead of doing actors, of doing message passing. Of course, it's more expensive to send a message to another machine as opposed to you make a call locally. It's much more expensive to serialize your arguments or serialize your return value, send it over the wire, deserialize, put it in the queue, execute. Of course, it's much more expensive than doing it locally. But you have no choice if you need to scale out. You cannot scale up and run a single machine. You have to go across machines. And once you cross the boundary, you already lost most of your benefits. You have to send this data. You have to send messages across the wire anyway. So it's sort of unavoidable trade-off. Just to quickly say, So Orleans was not built for scientific computations, just to be clear. It was built for scenarios that were sort of emerging, like social graphs, mobile backends. I mentioned Internet of Things, interactive entertainment, which is a fancy one I learned a couple of years ago, where people want to participate in a TV program as it's going on. So they use their tablet to vote or to kind of somehow influence the outcome. So it needs to, again, happen in real time or soft real time. Just we don't offend the actual real-time people. So we build it for these scenarios. But we think there is a lot of opportunities for scientific computation. And instead of prescribing instead of preaching, saying, this is where we think you should use this kind of system for scientific computation, we intentionally want to leave it open and up to you to come up with the scenarios that either involve high-scale compute, distributed compute, or modeling where you need stateful compute. So we discussed some of the ideas of the reception, but really want you to drive what's doable here. I think I covered this all. I can skip it. So just the summary. Developer productivity, we do get data, we do have data that's improved, and people are conservatively saying 3-5 times less code to write. Optimistically, up to 10 times less code to write to build certain systems. So it's much faster, much less expensive. And it does scale by default. Even if you artificially create a bottleneck, it's easy to remove it in this kind of approach because you sort of already partitioned your state by going with fine-grained actors. So we've proven it in production for years, and now it's available outside of the company as a public preview. I think I have links here, yeah. And I think it was in the description of the project with links to the sites, but just in case. Okay, any other questions? I think we could cover some of them. Oh, there is a question.
So, at which scale does it make sense to use this kind of distribution? For example, maybe I have a service and I know that it will not grow up, and maybe I can code some standard non-threaded server, or maybe the overhead is not that big, so I can use your or even for small problems.
So yeah, it's an excellent question actually. And I even wrote kind of a blog post a few months ago after release preview that to benefit from Orleans, you don't need hundreds of machines or thousands of machines. Like you don't need Halo scale to benefit. You can scale. The moment you go over one machine, you already need to solve all the same problems, coordination between at least two machines. But interestingly enough, in a single machine case, you'll benefit because of a concurrency aspect. Because to be safe, you either need to use locks or be immutable, like use a functional approach. And in a way, this is a functional approach because when they make a call to another grain, we deep copy your data, it becomes immutable from the caller perspective. So I think there are probably cases where it would not make sense to use it in a single machine case, but I suspect there's enough of them that it will help you even in a single machine case. But then you also future-proof because once you grow out of the box, you're sure you can add more and it will still work. The same code will work. You don't have to rewrite it. Any question? Mono, the question about whether this can run with Mono. Somebody posted on the Codeplex, well, I know who, Richard Asbury in UK, that he was able to start it on, I think, CentOS and Mono. He hasn't tested, so he just got some message processed correctly. So I'm guessing it's runnable, but I cannot guarantee it.
Okay, so one of the projects that are in the list of suggested projects is to use Orleans to build a small version of something that is, how many people have heard of something called Facebook?
It's a small company in the valley.
Microsoft has a product, so we don't Facebook. But anyway, you can build your own small version of Facebook. That's one of the projects. And so tomorrow, Sergey will go in deeper into Orleans.
It's the actual programming of Orleans, yeah.
Right. Something more than Hello World.
Yes, yes.
So now we have a coffee break for half an hour. And then who's next? Jeffrey Fox will give the next lecture starting at 11. And I was going to try to find out what happened to the list of projects. It's supposed to be on the website. I'm going to dig next thing I want to get